Okay, welcome back for Module 8, Day 8. Yesterday we had an exercise around the modifiers, and today we're going to be talking about the animation time and the control plugin type. And before we get into that, let's go through the exercise from yesterday. So first of all, most of the code that you needed to put into the skeleton was provided. So hopefully you were able to get the modifier working very quickly and easily. I'm just going to go through a few things to pay attention to. So we're in the modifier. So exercise 7 was derived from the standard modifier. We talked about what the difference is between the regular base modifier and the simple simple mod 2 modifier. So simple mod 2 uses a deformer class, and it's a little bit more complex. But in the end, the way the modifiers function is the same. So first of all, you should have noticed that we have a channels used API implemented, and it's our channels are the geom channel and the topology channel. We didn't actually affect the topology of the mesh, but this is how the skeleton is set up. The channels changed is the geometry channel, and again what we did affect was the geometry channel, so that's why this is set up this way. And this is actually the default, again, the way the wizard created it, so we didn't have to make any changes here. So this is one of the more common ways a modifier works, so that's why the skeleton code is set up to work this way. And then the input type is important. So we have to say that we can support deformable objects. Okay, so when something is selected, 3ds Max calls this when the modifier has become available to the user in the user interface, and 3ds Max will call this to see which modifiers are available for that object that was selected. Okay, and then there's the modify object, and that's where the bulk of the work goes in. We also had to update the validity calls. Okay, and we'll take a quick look at those. And that was essentially it. It already had a single parameter block, so we didn't have to really change the parameter block handling. So let's take a look at the implementation. So first of all, these are our params. And we have one parameter that was created by the skeleton, and I asked you to update that to hold a value that would contain the tension value that we're going to modify on the mesh through the modifier code. Okay, so I updated mine to be pb_tension. There's the text. I updated the string here. It is animatable, and so default 0, range -10 to +10, and the incrementer was 0.1. You had to change the n to be p_n, but I think you're familiar with that now. And then here's local validity. Okay, so we basically had to update this so that by default the validity gets returned either never or forever. And so we want to have a real validity, so we're going to use our own internal implementation of validity. Okay, so there's our interval, and we just return that. So let's take a look at get validity. And here you can see that we're actually using the parameter blocks to get the validity. Okay, so this is the data that's associated with the modifier and how it changes. So it gets the value at a specific time, and it checks to see what that validity interval is. Okay, so the get value will return the interval, and then we can just pass that back. Now if you had multiple parameters you have to kind of sum all of that together so that you get the validity interval that's the smallest, so that the other things that need to be updated are considered. Okay, so hopefully that makes sense. And then the last part of it was the modify, and here's modify object. Alright, so you can see the mod context is passed into you, the object state is passed into you. So you have the object, the mesh itself, or the object state, at a particular time with its mod context, and you also get to know which node it belongs to. Alright, so you can see you get a lot of information that's handed to you when the modify object is called. Excuse me. So the first thing we do is we get validity, and then we combine our validity with the channel validity of the channel for geometry and the topo. Okay, so this is where we're intersecting it down so that we have the correct validity interval. We get the tension value, and we then check to see if the object is a subclass of try-object. We could have also used the convert style here, and that, either way is fine, to see if we could convert it to try-object. So in this case, it's got to already be a subclass of try-object. We cast it to try-object, and then that gives us the ability to pull the mesh, and then we can do the operation. So the deformation all occurs on this one line, because all we're doing is we're taking the mesh and we're changing the edge tessellation tension value. Okay? So this will change the geometry, and so then we need to notify the dependents. Okay, and we're touching the geometry and the topo, so we need to send those. And then we also need to update the validity on the object for the geometry and the topo. Okay, so not too difficult. Not a lot of code was added, but this stuff, until you actually start working with it, see the behavior, you just need to work with it to really understand it fully. All right, so we'll switch back over to the presentation now. Okay, so today we're going to talk about animation, time, and controllers. And the goal here is to discuss in detail how to develop a control plugin. And we'll talk about the different types of controllers that you can create and that you can actually work with, the ones that are provided by Max. And then we'll also take a look at time and intervals again. Okay, so some of this is going to be review, but I think it's important to talk about it in the context of our animation topic. So first of all, there are two types of controllers. There's a keyframe and a procedural. So the keyframe controller will set the value of the controller at important key points in time. Okay, and that's why they call it a keyframe. So the controller provides all the values at other times by interpolating between the key values. So it's the controller's responsibility to calculate and provide the time at any point in time. Calculate the value at any point in time. Then the other type is called a procedural controller, and it computes the value at a certain point in time based on a programmed effect. Okay, so there's some sort of algorithm behind this, and it will calculate at any time requested. So these are the controllers that are part of 3ds Max, and they're based on value. And the superclass ID is provided here in a list. So we have the float, the 0.3, which also includes the color values. So color is typically represented as a value of 3 separate values, RGB. Position, rotation, scale, the transform, which is the matrix 3, morph, you can have a user-defined, then there's these two other ones that are master points and master blocks. So the principal classes for the controllers are listed here. So the control is the base class that's used for the creation of controller plugins. The SDD control provides a simplified way to create controller plugins. So at this level, if you subclass from this, you'll have fewer methods to implement, but you also get a little bit less functionality. And then there's the iKey control, which is used to access the properties of the controller. So this is an interface class. So standard 3ds Max plugins support this interface. So any of the existing controllers that are part of 3ds Max, you can use this interface to get access to them. Okay, so when you're developing your own controller, we're encouraging you to also implement it and support it by your plugin. Okay, and then the set XForm packet. This is used to allow a transform controller to know what is being specifically moved, rotated, or scaled. Okay, so basically what's happening in terms of the transform. And then the next one is the ease curve list. Okay, so this one varies the timing of a superior function curve. What that means is basically that a normal function curve charts an animated parameter over time, whereas an ease curve charts changes to the time of a function curve over time. Okay, so a 3ds Max user may apply multiple ease curves to a parameter, and this class holds a list of the ease curves and allows developers to access the data. So you'll be able to directly access what these ease curves are. And then finally, the mult curve list it's basically the scale factor applied to the value of its superior function curve. So this class holds a list of multiplier curves and allows you to access that data. So there's certain interfaces that are implemented by the built-in controllers, so you can see them listed here. So for example, at the bottom there, the LookAt controller has an interface called iLookAtControl. So all of the built-in ones have some sort of interface that allows you to get access to them. So the point rotation scale, or the PRS controller, is the default controller assigned to objects when they are created. Okay, they use subcontrollers to create the final transformation in the order. And this is kind of review from the transformation talk. First the position controller is evaluated, then the rotation, and then the scale. So that's the order that the final transform is built up. So let's just take a quick look over in 3ds Max at the fact that this is created whenever you draw an object. So I'm just going to draw a box here. I'm going to the graph editors. I'm going to pick the curve editor in track view. And you can see the box is selected, and here's the transform controllers. There's a position, rotation, and scale. Okay? So those, the listing of the controllers in the UI also correspond to the order in which the transforms take place. So that's a good way to remember it. I'm not sure if they planned it that way or if it just happened to be alphabetical the way they lined up, but it is convenient that you can see that they're lined up in the order in which they're evaluated. So let's talk about constraints. So constraints are made up of a subset of controllers that reference another object. So an example, here's some examples: the position constraint, the orientation constraint, link constraint, and path constraint. So these are generally accessed from the motion panel, or you can go to the animation constraints menu. So controller data access. So there's different techniques based on the type of controller. So if it's a keyframe, there's one approach. If it's procedural, there's another approach. So for keyframe, So position and scale keys are stored in the local coordinate system of the controller. Each key is independent of the others, and then the rotation keys are also stored in local coordinates, but each is stored relative to the previous key in the track. So rotation is additive, basically. So the computed rotation keys will be the absolute quaternions for each key for that controller. Okay, so it gets built up through the time. So then once the data is built up, then everything is then relative to the transform for the controller itself. So if you could call control get value, that's going to give you the transform of the controller, and all of this is relative to that transform. So the key data is returned in the local coordinate system of the controller, and the key values that appear in the key info dialog for a controller are in the local coordinate system of the controller. Alright, so both the data and the way it's shown in the key info dialog are the same. Okay, the only difference is we do display rotation in degrees, so we display it in degrees, but we store it in radians. Okay, and that's kind of a typical thing with 3D apps. So if we take a look at the interface for the key control, it basically provides this interface into the TCB, the Bezier, and linear keyframe controllers. And this allows add, delete, retrieve, and update of the keys of the controller. And this is all implemented in the istdplug.h file. Okay, so I'm just going to switch over to the help system. And the first thing I want to point out is that this is a versioned set of interfaces as well. So the latest one is actually Key Control 2. Okay, and so it has some functionality here, and then it's derived off of the base iKeyControl class. Right. So here you can see all the different things that's provided. There's specific interfaces for the different types of keys. So here's the linear float key, here's the linear 3.3 key, linear rotation, linear scale. Alright, there's then Bezier versions and then the TCB versions. Okay, so there's a good example in the import-export routines. The 3ds export.cpp has some good examples of this. Okay, so let's talk about keyframe interpolation. So interpolation between the keys depends on the type of controller. So the controller itself figures this out. Typically a cubic, which would be like the polynomial of degree 3, typically cubic splines for interpolation are used. Rotations are done using spherical linear interpolation, and this is commonly referred to as a slurp. And you do not use the iKeyControl interface to get keys and interpolate them in world space. Okay, let's think about that for a minute. Why can you not use the iKeyControl interface to get the keys and interpolate them in world space? So it's fundamentally because the keys are interdependent. So if we look at an example, let's consider scale keys as an example. In world space, scale keys are dependent on the position and rotation of the controller as well as any parent transformation. So this is because first an object is scaled, then it is rotated, and then its position is applied. And then the parent transformation is applied. So the scale is rotated, and if you scale an object along its x-axis, then rotate it, the scale becomes rotated. So the scale is no longer rotated about the world x-axis, it's rotated about some other axis through this transformation. So this is normally what you want because you don't really want the object to rotate through the scaled space, which would cause it to skew and look twisted. Okay? So it's hard to talk about scale in world space. It just when you think about it logically, it doesn't quite work. Okay? So another way to look at it would be if keys are put into world space, then interpolated in world space, the resulting animation is going to be different than what you would typically see or expect to see. So for example, consider an object that is rotating 360 degrees around its local z-axis. Okay, the key here is its local z-axis. And it's also tilted at some arbitrary angle. So if you interpolate the way that 3ds Max does right now, all the interpolation is done in the local coordinate system, and therefore the object will rotate around its local z-axis, which also happens to be tilted. So if we were to take a step back and try to interpolate this in world space, the rotation would occur about the world z-axis. The object will still, end up in the same ending position, but the path that it goes through will be different, okay, because of that arbitrary angle. So the summary is basically that you need to understand, the way 3ds Max works inside with computing its node transformation, and that it's based on the keyframes, and then you need to use that information to interpolate between keys accordingly within your own apps and within your own applications of that data. Alright, so there's some really good documentation about this, and if you have questions, I would encourage you to take a look at that, and again, take a look at the controller samples to see how they're handling it. So we'll take a look at some sample code in a moment, but before, let's just remember that the procedural controller, you must sample the controller to get the data from each required frame. And with the keyframe controllers, you will use the iKeyControl interface when appropriate. So let's switch over and take a look at the sample code. So first of all, I have a model open that I created ahead of time. I'm going to go into the track view, and I'm going to select this box. And if you remember that, basically any object that's created in the scene are going to get default controllers. So in this case, for example, the position controller, let me click it and open up the assign. You can see here that the caret, the current controller, is set next to position XYZ. Okay, so that's the default one. It is a procedural style controller. Okay, so when I move through my animation, you can see that I've got three keys total, the start, the middle, and the end. And that's how that controller works. Now, if we want to look at its data, I'm going to go into a utility object here that I created. I'm going to click Controller Data, and now I'm stepping through my code. So let me clear this output window first. So the first thing I'm doing is I'm getting the selected node. Okay. And then I'm going to go ahead and get the control. So on the node, there's the get TM controller, the transform controller, and this is a container for the other controllers. So within that is the position controller, the rotation controller, and the scale controller. So we're going to work with position in this example. So I'm going to go ahead and get that. Now I'm going to output some class ID information about this just so you can see, and you can see those are that's the data. So I've got a class ID of this and a super ID of this. Now something that's interesting about the procedural controllers is that for whatever reason they don't define actual class IDs in the SDK, so there's no predefined class ID. So when you want to look positively at the controller to see what it is, you can just define it yourself, and there are other samples that do that. So it's not always necessary, but in this example I just want to positively identify it for you. So I've got the control now, and what I'm going to do first is I'm going to try and get the interface. Okay, so I'm going to call get key control interface, and if it has the interface, I'm going to get an iKeyControl back. Okay, so that is null. Okay, so that means this is procedural. So we're going to step into this block, and here's the code that actually positively identifies it as the position controller. And then I can do things like get the key time directly from the controller. I can also get value directly from the controller. Those are the two operations that you would typically do to get the data. So in order to do some calculations, I'm going to determine the ticks per frame. And then I'm going to step through this, and you're going to see that there were 3 keys. So that was 1, 2, 3. Okay? So the data that we output is down here, and you can see that at position 0, default slider time 0, I have minus 2.4 and so on. So there's the XYZ data. So the time was obtained here, and then that time is passed into the get value, and then what I can do is I can get the exact location, the position at that point in time, which is equivalent to where the keys are set. Okay, so I have one set at 0, one set at 15, and one set at 30. Now, that's given me the procedural value. It just happens to be at the times where the keys are set. Now, what I can do is I can actually go through and I can get the value from every slide as well. Every tick, every piece, place, and time. So I'm going to do that next. So let me just run through this code. Okay, so the first thing I did was I got the start animation from the animation range API, and where it ends. Okay, so I'm getting the current segment, and then I'm going to output the position at every frame. And you can see here's the calculated procedural data at every single frame all the way through the entire animation. Okay, so you remember my key stopped at 30, and so that's the last value you're going to see being changed. The rest of these all the way through to the end is 100 frames. Those values didn't change. Okay, so I was able to get not only the value at each key just using these basic APIs, but I was able to get the value at every tick of time. Okay, so that's a procedural. So let's just run that to the end. Okay, and remember it was 0, 15, and 30. So this is the default when you create an object and you add keys to it, okay, without changing its controller. So now let's take a look at a keyframe version. Okay, so this one is a sphere, and you can see my position controller is different. It no longer has the XYZ value. And if I go into the Assign Controller dialog, you're going to see that it is a linear position. Okay, so I've changed the controller to be a linear position controller. And you can see even in the curves that it's a linear movement. Right? So now if I run this, same code, you're going to see that now the iKey control has something. Okay, so I've got a interface, so now I can use that interface to figure out what I need to use more. So I'm jumping down here, and I also need to know which type of controller it is, so I can use the appropriate sub-interfaces. So is it a TCB? Not in this case. Is it a hybrid, which is the Bezier? Not in this case. Is it linear? Let's hope so. So when I step into that, you'll see it goes into the linear code. And so right off the bat, you're going to see, oh, there's another specialized interface. In this case, it's called iLin.3 key. So there's a specialized interface for holding the values of these keys as well. So what I'm going to do is I'm going to step over that. I can get the number of keys. I go back to the interface to get the number of keys. And then I can step through each key, so get the number of get the ticks at that key time, okay? And then within the interface, get the key at the index, okay? So I've got a certain number of keys. I can walk through them in their index order. So let's just run this. I should have 3 again. Okay? So let's look at that output. And here you can see the class ID is different, so it's definitely a different control. Its superclass is the same though. So it's the same type of control in that it's a position controller. And then here you can see at 10, 20, 30, I've got these values that came off of this linear position key, okay, which is this interface. And that holds the value for X, Y, and Z, and it may hold different values depending, and that's why these interfaces are unique to the control itself. Alright, and we'll just show one more example here, and this is the cylinder, and again it's a different controller. In this case it's the TCB position, and if I run this code, let's just go down here, let's run the cursor, and is it a TCB? In this case, yes it is, and in this case I've got an ITCB 0.3 key, so it's a different interface to hold the value again, and I basically can get the data in the same way. So if we look at the output, there's the data for it, and this one happened to have keys at 6, 14, and 24. Okay, so 6, 14, and 24. So pretty straightforward. It's just a little bit complex in terms of figuring out which controller you have. Okay, and that's the key, no pun intended, to figuring all of this out, is just to make sure you understand which controller you have, because first of all you need to use either an interface or access it directly, and if you're using one of the interfaces you need to know which one it is so that you can get the actual data from it properly. Alright, so now we're going to talk in more detail about intervals. So again, it's a class that represents a length of time. A validity interval is used to describe a range of time over which an item is said to be valid within the cache system. So you remember we talked about this in the geometry pipeline discussion, also in the modifiers. So that's where the object and modifier plugins are responsible for maintaining, updating, and reporting their validity intervals. So these intervals are then handed over to the cache system, and things like animation then are updated to handle the actual cache system updates of the things, only the things that really need to be updated. So it's an efficiency performance thing. So retrieving interval values, so there's a get value method of iparam block that's a reference to an interval. It's frequently used to calculate the validity interval. So your parameters are the things that you want to validate. And the periods of the interval include these concepts, which is basically a parameter that is constantly changing is instantaneous. A parameter that does not change for a certain period of time, the interval will be longer. And parameters that never change, the interval will be forever. Okay, so a fixed parameter is going to have a validity interval of forever. So if we take a look at this example, so first of all, this line down the middle is what we're looking for. So a validity interval is being computed at time 40. And this is an object with two animated parameters that are called radius right here and segments right here. Okay, so the interval is computed by first intersecting an initial interval of forever with the radius parameter. Okay, so forever includes time from negative infinity to positive infinity. That's what forever means. So we intersect those two, and the intermediate result is from 20 to 100. That's when the radius parameter can be changed. Okay. So, that gives you the result of 20 to 100, and then the interval is intersected with the segment parameter, which is from 10 to 50. Okay, so the result of this intersection gives you 20 to 50. Okay, so this is the intersection of both. Okay, so the validity interval of the object at time 40 is from 20 to 50, to consider both of those parameters. Now, if this line moved down below 20, then it'd be a different result. It wouldn't have, it would just be the 10 to 20 value in the segments parameter. Okay? So let's look at these methods and what they do. So first of all, the object validity is implemented by a plugin and returns the validity interval of the procedural object around the time passed. Okay, so the method, this is computed by the object starting at an interval of forever and then intersecting this interval with the intervals of each of its animated parameters. Okay, so we saw that in the last diagram. So in this way, basically the interval is then whittled down as it is intersected with each of the parameters, with the resulting interval representing a period of constancy about the time value passed. So the interval represents how far before the time value and how far after the time value is the object constant. So then local validity. Okay, so the local validity returns the validity interval of the modifier itself around the time passed. So in general, this would be the intersection of the validity intervals of all the controllers in the modifier that used to control its parameters. So if a modifier was not animated, this interval would be forever. And we saw local validity in the modifier example code. So get validity, and this was also used in the sample code from yesterday. So this method is called to retrieve the validity interval of the modifier, and the modifier provides this interval by starting at interval forever and intersecting each parameter. And that's why we could use one to call the other, because local validity and get validity are essentially the same. So most of the time they'll return its implementation of local validity. Update validity is a modifier will call the update validity method of an object when a modifier is applied to an object. It needs to include its own validity interval. So frequently this is called by the modifier in its modify object method. Okay, and so this is to notify or update the validity as things are flowing. And then set channel validity is called to specify a validity interval for a certain channel of the pipeline. And so this is what whittles it down even more to a certain aspect of the geometry that is valid. So that takes us into time functions, and I'll remind you, we talked about time in the beginning, but here there's a little more detail here. So they're stored internally as an integer number of ticks, and each second contains 4,800 ticks. And the reason that this value was chosen is that it works well for the common frames per second standards that are used. So 24 frames per second in film, 25 in PAL, and 30 in NTSC. So I'll remind you that the ticks has to do with time. So if you go to 3ds Max, there is a dialog here that is the time configuration. And the time display over here is typically one aspect of it is down here on the slider. So I currently have mine configured to the default, which is frames, but you could also change it to one of these other time displays. Alright? So that's for just for the user interface. Everything internally is stored in the ticks. And then also there's the frame rate. So we talked about basically these three being very compatible with that 4800 number. So the time value stores the number of ticks that the time represents. So it can be displayed as frames, SMPTE. So this is the minutes, seconds, and frames. Frames and ticks, which is an integer number of frames and the number of ticks, or minutes, seconds, and ticks. Okay, so we just saw those in the time dialog box. So methods to work with time, so there's the get time display mode and set time display mode. So you can actually update those UI components from your plugin directly. So those things that are part of that time dialog are what we're talking about here as far as API methods go. Okay. You can also determine what the ticks per frame, and you can set the ticks per frame. So you saw me use this in the sample code earlier. The get frame rate and set frame rate deals with the number of frames per second. So it's an alternate way to specify the number of ticks per frame. Okay, so this is going to affect this. And then finally, time to string and string to time. And these are convenience functions that will allow you to work with strings in a very convenient way and get it actually back and forth into this time value. And then that leads us to animatables and sub-animatables. So animatable is the base class for anything to animate. And if you remember back to the very beginning, we looked at the class hierarchy, and animatable is actually right at the top of all the objects that are in 3ds Max. I mean, anything that can go into the 3ds Max scene and parameters, all of that stuff, all of those things can be animated. So the animatable is the base class. It contains methods related specifically to the track view. Okay, so in order for the track view, which is where you can control animatables, you need to implement certain methods. Sub-animatable is an object managed by an animatable. So an animatable is going to have a collection of sub-animatables. So for example, a parameter block is a sub-animatable to, for example, a parameter is a sub-animatable to a parameter block. So there's these fundamental methods, which is the number of sub-animatables, the sub-animatable add an index based on the total number, and then sub-animatable name. And this one is really important because this is what the UI uses to display the component in things like the track view. Okay, so if you forget to implement the name, you're going to have empty things showing up in the tree view, for example. So the node contains 6 sub-animatables. So there's the space warp bindings, there's the transform controller, and that's a really important one. There's the object reference of the node, and that's a really important one. The material, the visibility controller, the image motion blur controller, and if any of these are not assigned, they will be set up as null, and they will not display in the track view if they're null. So here's a good example from the track view. So we have the transform controller here, and the object itself, the geometry. Another good example over on the right. Here's a box that has space warps bound to it. It's transform. There's the modified object. So there's the modifier stack. And then there's some materials as well. Okay? So these are all animatable things. So to enumerate and identify sub-animatables, you have to implement these things. So you have to implement the number of subs, the sub-anim you return at the index being passed to you, the sub-anim name, which is an index being passed, you return a string, And then you have the option to bypass the tree view if you don't want your object to show. And then there's the sub num to ref num. So this last one is used for basically being able to copy in the tree view. So if you return -1, then it won't be copied. But if you want it to be copied, what you do is you provide the map from the sub animatable to the actual reference, the object, and then internally 3ds Max will copy the referenced object and make a new one. Okay, so that's optional. If you return -1, then it does nothing. So then just some miscellaneous things here about the animatable. So there's an animatable handle, and we looked at this in the in one of the earlier presentations as well. It's basically a unique identifier for any animatable object. So all animatables have this anim handle, but they are at runtime only. So they're not filed to the file, to the model, to the scene file. They're ideal as key values when sorting animatable objects. So if you're looking for animatables, it's a convenient way to look for them. So these are not node handles, so don't confuse them with that. And then there are some methods, get handle by anim or get anim by handle. So that's the interchange to give you the handle or the animatable. So because these are stored separately, it's basically a key value lookup system. So there's a key that's the anim handle, and the value is the object itself, the animatable. So for track view, by default, the animatables do appear in track view. And again, you can bypass the tree view, implement that function to return true, and it will not appear. And then there's the copy and paste operations, which is something we talked about with that sub anim to ref num operation. There's a whole series of time operations. There's drawing and hit testing for the tracks and function curves. So there's a way that you can work with the mouse in the track view to do hit testing for your own curves. There's key operations, and then it can also be deleted from the track view if you want. So those are the behaviors that you can implement and have track view handle for you. There's also the concept of trajectories. So this is the display. It's basically displaying the path that an object takes over time. So this is accessed from the motion panel it's a UI element. So if you want to support trajectories, you override specific methods. Okay, and so these are like the little icons that show how the curve would be represented. Okay, so there's different ways of handling that with these interface functions. There's also track locking, so you can lock a track to prevent editing of animatable parameters. The ParamBlock 2 directly supports lockable tracks, and if you're going to use this, consider supporting the iLocked track interface. So there's a topic in the documentation, and you can see the iLockTracks.h file, and there's a sample. There's several samples in the controllers section of the SDK. And then one other thing that you need to be concerned with is reference messages during animation. So typically message system is quiet because of validity intervals, but the caches are the exception when they're discarded. So you might get the ref message object cache dumped is sent when the cache is discarded, and then in a controller you want to handle that message by stopping the propagation of the message by returning ref stop. Okay, so that just mainly says, okay, you know, we need to update, and I've handled it. The first and last keys in a track define the valid animation, and so there's an out of range type. So before and after this range is considered out of range, and is denoted by the out of range type. and this is also known as the ORT, and you can see that there's different out of range values that can be used. Okay, so let's take a look at some example code. So I'm going to switch over to Visual Studio, and you can see that I have some sample code open. This is directly from the SDK samples under the controllers subdirectory, and this is the Euler rotation control. So you can see it derives from lockable control, which is a specialized version of control. And the first thing I want to point out is that if you remember back when we talked about the get transform control is a container for other controls like the position controls. So the same is kind of true here. So for the rotation control, it's going to contain different subcontrols that will hold the values. So in this case, a rotation for the X, a rotation for the Y, and a rotation for the Z. Okay, and then when we scroll down a little bit, you're going to see the number of subs here, and we're returning 3. The sub animatable is implemented, and the sub animatable name. And the reason it's returning 3 is that, well, we have 3 sub controls that are providing our values. So we'll switch over to the CPP, and first of all, notice that they just have some defines that index their controls. So this is a set up as defines, but you could also make that an enum, and I think the enum is a little bit more modern. So the next thing I want to show you is the sub anim. So here you can see that sub anim is being called, and it's passed into you, and you return the control or the animatable at that index. Okay, so in this case, they've got a function here that's called subcontrol, and whenever that is called, it switches based on the index coming in, and if it's Euler xref, then they return rotation x. If it's y ref, it's rotation y, and so forth. And so that corresponds, these are the actual controls that are part of the class over here. Okay, and I also want to show you anim name. So here's the sub anim name, and you can see it's also very similar, except in this case it's returning the string that represents it. And this is very important for the user interface. Okay, and so because we're a reference target and a reference maker, we should also look for get reference and set reference. Okay, so let me just show you the implementation here. So here you can see it's the same idea because we're referencing 3 controls. So in the case of Euler xref, we return that control for rotation x. Same for set ref, we set up our relationships here. Okay, so we now have references to these sub controls. And then we should also look for the values. So we have a get value and a set value. So you can see the get value is here, and it looks very similar to what we showed in the code where we were getting data from one of the existing controllers. So you have to calculate the value at a specific time. The value is filled in and passed back. You get a validity interval, and if there's some extra things, the get set method is passed in. Okay, so in this case, I'm sorry, not extra things, but the get set method will be either control relative or control absolute. So by default, they calculate the absolute data, and then if the method should be relative, then they translate that through a matrix to make it relative. Okay, and then the value is created and passed back. All right, and then the set value is right here, and you can see that in this case it's It's very similar in terms of its signature, but there's quite a bit more code in this one to figure this out, okay, and actually set the value. So this is the fundamental behavior of this control. The implementation of this control's what it does is essentially in this method. Okay, so I'm not going to show you the details of that, but you get the idea that set value is where you're going to calculate what the control does. Okay, so now let's talk about the exercise. So we're going to develop an animation controller. So the first thing you'll do is use the wizard to create a plugin that is a controller type. So this controller's basic functionality is going to be that it does not support the Z-axis positioning. Okay, so this will limit the animated movement to be in the XY plane only, and this is all absolute to the world coordinate system. And when you create this, the wizard is going to complain. It's going to say that the wizard does not fully support controllers. But the good thing is that it does give us base class implementation. So go ahead and say OK, let it create the skeleton as is. So there's some instructions here to kind of clean up the class to get started with. And then what you're going to need to do is add the controls that are part of this container. So you remember in the Euler it had 3 controls. We're going to add 2. Okay, and you can add an enumeration to handle the indexing. And then you have to update the exercise 8 constructor to initialize everything properly. And you'll notice that we're using replace reference, and there's the instructions and reasoning for that here. Implement the destructor to clean up, because we are now a reference maker. We need to talk about, we need to handle that. And there's the set reference and get reference code that you must implement. Okay, so this is all just kind of base stuff to get the control to start working. You also need then to implement get and set value, and this is kind of the core functionality of the controller itself. And then finally you'll implement the sub-animatable methods. Okay, so all of the instructions are in here. Again, it's kind of taking you through it, holding your hand, but again, I think it's really important to have a successful exercise rather than getting stuck. So, feel free to let me know if you have any questions, and we'll go through the code in detail tomorrow first thing. Thanks very much, and we'll see you tomorrow.